Hi, this is Chuck Stull, continuing our look at the technology industry with an in-depth look at semiconductors. Now, semiconductors are the basic component of modern electronics. They're inside computers, cell phones, flash memory, digital cameras, iPods, iPads, medical equipment, all kinds of military equipment, even household goods like dishwashers and dryers use these components. Now, the earliest computers used mechanical switches, like a light switch, or vacuum tubes to represent the on and off or 0 and 1 of binary code. In 1947, Bell Labs, a subsidiary of AT&T, who we've discussed earlier, developed the transistor. Now, the transistor was an electronic switch, and it replaced the mechanical and vacuum tubes using much faster speeds, less power, right? Overall much more efficient. And AT&T, partly because of the consent decree we had discussed earlier, licensed the transistor to many other companies. The next step in this industry was the development of the integrated circuit. This put multiple transistors and other components together on the same chip. Now, in 1959, competing patents were granted to Texas Instruments with Jack Kilby, Fairchild Semiconductor, Robert Noyce, both for the integrated circuit. There was a patent fight between the two, and it was settled with a cross-licensing agreement. Each could use the other's patent and settled that argument. Now, the integrated circuit is the basic component of modern electronics. Memory chips and microprocessors are integrated circuits with millions of individual components, as are camera sensors, graphics cards, and other specialized chips. Now, the early chips had dozens and then hundreds of components, but chip production has been characterized by rapid technological change. And this has been a driving force in today's economy. More components, faster chips, smaller and smaller, more efficient. Gordon Moore, co-founder of Intel with Robert Noyce, published a 1965 paper on this in the journal Electronics, and he had observed a doubling of the number of components about every 18 months, and he predicted this would continue. This prediction is known as Moore's Law, and since the 1960s, the industry has experienced this kind of growth in line with Moore's prediction. And this has become widely accepted and even expected. Now, if you look at this graph, notice the scale on the left, the vertical scale, is growing really rapidly. This is a log scale. If we were to do these on just a normal graph, the number of components would quickly disappear off the top of your screen. So Moore's Law, first observed by the founder of Intel, and then later a goal by Intel, is that they would try and progress at this rate. Now, eventually, we're going to reach the point where Moore's Law is going to be limited by the size of atoms. The widespread interpretation is that we will continue to see faster and cheaper electronics. Now, while modern chips have millions of components, the entire package is tiny, and the production of chips is a demanding industrial process. But the basic procedure is fairly simple. The chip design is printed onto a layer of light-sensitive material on a silicon wafer by shining UV light through a mask. The wafer is then etched, much like photofilm, but much more precise. Now, the process is very demanding. Even tiny contaminants ruin chips, and humans create lots of contaminants. Walking through a room, a single person will create millions of particles in a minute. And that's the reason why we see these clean rooms and bunny suits, very expensive procedures. You can easily find, if you're interested, much more information on how the mechanics of producing chips works on the internet. But essentially, we start with a silicon wafer, or a fab plant starts with silicon wafer. They print the design. They then test and discard the imperfect chips. And after 8 to 12 weeks of processing, they end up with a large batch of chips of whatever particular type they have. As you might guess, there's a huge setup cost in terms of designing a new chip, and that will lead to economies of scale. An individual company will spend hundreds of millions of dollars for each new chip and then essentially print replicas. Right? And so the more production we have, the lower the cost per chip will be, right? And so there's an advantage to large-scale production. As a result of that, we would expect to see, and do see, high market concentration. Single firms with over 50% of the market are common, and frequently we have only a few major producers in any market segment. If we look at some of the major market segments, we can see that a small number of firms dominate them. So Intel, in terms of microprocessors, and we'll look at them in more detail, Samsung and Toshiba for flash memory, Samsung, Hynix, and Micron for the dynamic random access memory chips, and Qualcomm for the smartphone chips. And those are all based, mostly all based on British design, the ARM licensed architecture, and it's used by other chip makers as well in things like tablets and smartwatches. I want to look a little more at the production process in our next video. But for now, this is Chuck Stull from Kalamazoo College talking about semiconductors and microelectronics.